Let's see an example of solving two coupled equations to find the values of the variables that are common between those equations. This is something that turns up quite often in the world of solving physics questions. Here's the setup we discussed in precept today. We have a mass of 40 kilograms and it's suspended in this funky fashion. There's three strings, one off here at 37 degrees with respect to the horizontal, one at 14 degrees with respect to the horizontal, and the third string, which is actually holding the mass, is hanging straight up and down. Let's denote each of the strings with a particular variable, so we'll call the tension in this first rope hanging vertically as T1, the tension in the second rope here is T2, and the tension here as T3. We can look at two systems when we set up the equations. First would be to look directly at the mass that's suspended. The second would be to look at just the knot instead. Now there's no mass associated with the knot, but we can still look at how the forces all sum up to be zero here. Keep in mind the whole system is not accelerating, therefore at any point in the system the sum of the forces must turn out to be zero. Let's consider the mass first. In this case, what we're saying is that we have a mass, and acting on that mass are two forces. One would be the tension of the string, let's call that T1 on the mass, and that's acting up, and the other is the force of the earth acting on the mass. Those two forces should be the same, after all the mass is not moving, and we can very quickly write down some equations. Here then, the sum of the forces in the y direction should be equal to 0. I've denoted the positive direction as up, and so we can say the sum of the forces would be the magnitude of the tension on the mass minus the magnitude of the earth force on the mass, and all that should be equal to 0. Then we can just write down that our tension acting on the mass is equal to the earth force on the mass. In this case, we have the simple model that the mass times gravity is the force of the earth on the mass, and that's approximately 400 newtons, using 10 meters per second squared for gravity. Let's consider now the forces at the knot over here. This is going to be our system. Okay, so here we have a force diagram for the knot. We notice that there is one string pulling off here at an angle of 37 degrees with respect to the horizontal. We're going to call that T2K. In other words, the tension of this rope on the knot. Same way we can denote T1K, the tension of the lower string here on the knot itself, and the tension of rope 3 on the knot at 14 degrees. So let's set up our equations. The sum of the forces in the x direction on the knot should be 0, and the sum of the forces in the y direction on the knot should also be 0. Looking at our force diagram here, we can just go through one at a time and set up all of the different terms that are involved in these two sets of equations. In the interest of time, I've written out the two sets of equations that we get from going through each the x and the y components. What we have then is an equation which just relates the x forces, that is the x component here of T2K and the x component of T3K, which happens to be in the negative x direction, so there is a negative sign on it, and the forces in the y direction, the positive component here of T2K and the y direction only is this term. The T1K is only in the negative direction, so we have a negative sign on that. That's T1K, and then T3K again in the positive direction over here. Keep in mind that T1K here, since this is a continuous string between this point and this point, T1K is exactly the same thing as T1M. That is, it has a value of 400 newtons. The negative sign here indicates the directionality. It indicates that the force is down. So, since T1K is the same thing as T1M, we can just basically get rid of this guy and put 400 newtons directly into this equation. So now we want to solve for T2K and T3K. To do this, we have a couple of different options. First option would be the most common one, and that would be to put T2k in terms of T3k using one of the equations here. So let me just start with this leftmost equation, and I will take the cosine of 37 degrees and put it on the other side of the equation so that we have an equation that represents the value of T2k in terms of T3k. You could, of course, choose to calculate the actual values here for these guys with your calculator and plug that in. That's fine, but I'm going to carry along the cosines with me for now. Now what we're going to do is take this equation here, the value of T2k, and plug it into this equation over here, and then we'll be left with an equation that's only in terms of T3k. So let's do that. Let's take this and plug it into this equation over here, in which case we get T3k cosine of 14 over cosine of 37, all times sine of 37, minus 400 plus T3k sine of 14 degrees is equal to 0. We can finish that off by taking T3k and bringing it on the outside of all of the other multiplicative factors, so we end up with cosine of 14 over cosine of 37 times sine of 37, and then we would add sine of 14, and all of that would equal 400. So what I did was just take the 400 term and I put it on the other side of the equation, so now it's plus 400. I've taken the T3 that's common to these two terms here, and I've pulled it out so it would multiply through to each of these two terms, and this way we have a way to solve explicitly for just T3 on its own. Now we're simply going to take the value of T3k as equal to 400 divided by, well, I need to evaluate all of this stuff here, and I can tell you, using my handy calculator, that the value is 0.973, and so that turns out to be about 412 newtons. We can now take this value and just substitute it back into this equation over here to figure out what the value of T2k is. And again, that's just a matter of putting it into the calculator and finding out it's about 500 newtons. Here's an alternate method. We could take our two equations that we had on the last page. Here I've just put the 400 onto the right side of the equation and put them on top of each other, like this. The goal of this process would be to do some manipulation to one or both of these equations so that when we add the terms together, that is, when we add the left side to the left side here and the right side to the right side here, that what we're left with is only in terms of one of the two variables that we don't know. Okay, so let me make a little room here. I'm going to pull this guy down here just a little ways. So the goal here is to be able to do something with this term and something with this term here, so that when we add these two sides together, what will end up happening is the T3k terms will cancel each other out, and we're left only with things in terms of T2k. So the easiest way to do that is to divide the left side of this equation by cosine of 14, and hence we have to also divide the right side by cosine of 14. And this won't matter to the right side. It'll still be 0. Since cosine of 14 does not equal 0, we're doing okay. We're not dividing by 0. So this is okay to do mathematically. Similarly, we could take the left side of this equation and divide it by sine of 14 and divide the 400 by sine of 14. In this way, what will end up happening is this part of this term here is going to lose its cosine, and this part of this term here will lose the sine part of it. We're done. Okay, so what does this translate into? These two equations now become T2k cosine of 37 divided by cosine of 14 minus T3k equal to 0. The cosine 14 from up here has now gone away, and we're just left with the T3k, the negative sign still on there. The other equation becomes T2k sine of 37 divided by sine of 14 plus T3k equal to 400 divided by sine of 14. Again, you could just go through with your calculator and figure out the values of the sines and the cosines and carry the numbers instead. Now what we're going to do is to add the left and the right sides of these equations vertically, this way and this way. Okay, so we're going to take this part here and add it to this part here, and we're going to put the result here, and that will equal this added to this on the right-hand side. So adding stuff together and combining some terms, I'm going to pull the T2k out, and I will end up with a cosine of 37 divided by cosine of 14 plus a sine of 37 divided by sine of 14. Close the parenthesis. The T3k here and the T3k here term, those cancel each other out, so we're left with all of this equaling 400 divided by sine of 14. If we carry this out, we're going to have to pull out the calculator, and what we'll see is this term on the right is 1,650 divided by 3.31, which is approximately 500 newtons. This is the same answer that we had before here. Clearly we can put this value of 500 back into one of our original equations and get a value of T3k, which will turn out to be, once again, about 412 newtons. Which one of these methods is better depends a bit on how the equations are set up. Sometimes it's absolutely trivial to use this technique and it saves you a lot of work. In this particular case, I don't think it saved you anything and would be just as easy, if not easier, to use this technique here. Most students prefer this technique of swapping in and then going back, putting back into the original equations. The choice is yours. You have to get the same result either way. It's whatever happens to be easiest. But do practice this technique of combining the two equations together and getting quick at doing it.